Okay, so now as I mentioned, we'll get into the practical section of the wind and seismic provisions. And where do we go once we get our demand on our shear wall, our demand on our system? Where do we find the capacities for our shear walls? Well, that would be, if we're dealing with wood structural panel shear walls, is table 4.3a. And for those of you that have a hard copy of the wind and seismic provision, hopefully you're following along and you can go to this section. But this is where we get our capacities for our shear walls, and this is pretty much a prescriptive table, meaning that you have to have a recipe to get the capacities that are shown in this table. You have to have a certain wood structural panel, a certain nominal thickness of your panel, your minimum fastener penetration, and then the fastener type, which nails are common or galvanized box nails. And then we move on down to the seismic columns. Now this is a truncated table in that there is also a B portion that is for wind. But this one, since we're dealing with seismic in this presentation, we'll just concentrate on that. So for this, we have panel edge fasteners spaced at 6 inches on center, and then we get our capacity, V sub S, for a 7/16 inch wood structural panel struck 1, and 8-penny common nails at 6 inches on center panel edge spacing. The framing is 0.5, the specific gravity of the actual framing, Douglas fir, and then studs at 24 inches on center. Now remember, I mentioned that you can go no greater than 24 inches on center. So we get a capacity, nominal shear capacity of 510 pounds per linear foot. The other thing to point out is when we are determining our deflection of our shear walls, we're going to need to know our apparent shear stiffness, which can be pulled from this table as well. So this highlights that two different columns, one is for OSB and one is for plywood. And for this particular shear wall, OSB is at 16, whereas plywood would be 13. So you can see that OSB is slightly stiffer than plywood for this thickness and this application. So that's one thing. I'll get more into the apparent shear stiffness later in the presentation. Now, important to this table are the footnotes to this table. I know sometimes people will tend to just go to the table, use the values in the table without understanding the assumptions that were made to create that table. So we're going to go over the footnotes to the table just to get an overview and an understanding of the background behind the table. And the first, and this is very important, is that this table is based on nominal unit shear values. And given that this is a dual format document, we need to reduce that value based on whether or not we're doing ASD or LRFD. And this footnote tells you where to go if you're doing ASD or where you're going, what section to go to if you're doing LRFD. Now, also, footnote 2, this deals with if you have, if your framing or your wood structural panel is 3/8 or 7/16, you can increase those values to the values of the 15/32, provided that your spacing your studs is 16 inches on center and, or if your panels are applied long direction across the studs rather than vertically. So an advantage, you can increase your values given these two different requirements. Footnote 3, this deals with the specific gravity adjustment, and I mentioned previously a 0.5 for the specific gravity for Douglas fir larch, and so the tables are based on Douglas fir larch or southern pine. If you have something other than those species for your framing, then they need to be adjusted by a specific gravity adjustment, and we'll look at that in more detail later. Now footnote 4, that deals with the apparent shear stiffness. It's assumed that the apparent shear stiffness is assumed that is based on the framing being less than or equal to 16% moisture content. Also, it's assuming that the OSB, you have OSB or 3-ply plywood. Now, if you have something greater than 3-ply plywood, you can have a 20% increase in your shear capacities. So one thing to remember. These are good things to remember if you want to get some little bit more capacity out of those values in the table. The other footnote 5, this deals with the actual framing of that wood shear wall, where it's being framed, and not where, but what is the moisture content of the framing members when it's being constructed. Now, if it's being constructed and the moisture content of that framing is greater than 19% moisture content, then the apparent shear stiffness will need to be multiplied by 0.5, meaning it's going to give you a reduction in that actual apparent shear stiffness, which comes into play when you're determining your stiffness of your shear wall. So something to be aware of. One more footnote having to do with the detailing of the panels when you have panels applied to both sides. I won't get into this now because we'll get into it in more specifics with some illustrations that will explain it. But it's where you have adjoining panel edges and shear walls on both sides. And then the last footnote has to do with, it's assumed that the galvanized nail shall be hot dipped or tumbled, and this has been in the this is an assumption that's been made for even going back to UBC, so it's nothing new there. Okay, now that we understand what the values of the table and what the assumptions were made for those shear walls, how do you determine the capacity of the shear wall? Well, as I mentioned from the footnote 1, if you're dealing with ASD or LRFD, it tells you to go to section 4.3.3. And right here, the top one gives you an adjustment taken from the table. It was 500, the nominal value was 510. To get it into an ASD value, you've got to divide by 2. Which is 255. Now you'll note that these values were what were published in the 2009 IBC. As Buddy mentioned, in the 2012 they no longer have values for nailed shear walls. So if you compare the values from the table, straight from the table, and what was in the 2009 IBC, they will be totally different. I've had people call me and say, I'm getting double the values of what I did in the IBC. Well, this is why, because it's a dual format document, and you got to divide by 2. Now, if you're doing LRFD, you multiply that 510 pounds per linear foot times 0.8. Okay, and I think I got to speed up a little bit and talk a little faster because they're getting slow on time. Now, I mentioned the adjustment for specific gravity. If you have something other than southern pine or Douglas fir, even though specific gravity for southern pine is a little bit more, the baseline is that the factor is 1.0 for your specific gravity adjustment factor. Now, you can see from the framing, our least wood member on this chart here is Western Woods, and it has a specific gravity of 0.36. So you can see it reduces the actual value for your shear walls because it has less of a specific gravity by about 14%. So something to be aware of if you're trying to, again, get more capacity out of that shear wall. You can increase it by depending on the type of framing that you're dealing with. Now, in addition to all of that, there are some aspect ratio requirements for wood structural panels, and just for this diagram here, for seismic design, this does not apply to wind, but for seismic, where you have a 2-to-1 ratio, and that's BS is the width of your panel, BS, and height of your wood structural panel or your shear wall. If you have a 2-to-1 ratio, there is no decrease in your capacity. You can go up to 3.5-to-1, provided that you multiply your capacity by 2BS over H. Now, this is going to be clarified a little bit more, or you'll in the 2015, there's going to be a slight revision to this based on some testing that is done, but more to come when you get into the 2015 wind and seismic provision. This just shows you a chart of a comparison depending on your width of your shear wall and what the width does to your capacity of your shear wall, meaning that the narrower your shear wall is, the less capacity you're going to have for that shear wall. And so for a 2-to-1 ratio, 8 foot high, 4 foot wide, we have an aspect ratio factor of 1.0. But if we go to the maximum limit of 3.5 to 1, you're reducing your capacity of your shear wall by 43%. That's quite a hit. So taking this into consideration when you're laying out your shear walls, you're not going to get that much out of those really narrow shear walls. And I realize sometimes the architectural design really doesn't give you any options. You've got to use that wall no matter what because you don't have the luxury of those longer walls. But just something to consider. Okay, so we'll do an example of a strength calculation where we do, going back to that same 510 pounds per linear foot capacity. Now we're using spruce pine fir framing with a specific gravity of 0.42 and the aspect ratio of 3.5 to 1. So we're trying to figure out what our capacity is using LRFD, and we'll also do ASD. So real quickly, our specific gravity adjustment for that spruce pine fir framing is 92%, so we're 8% reduction. And given all that, with the specific gravity adjustment, the aspect ratio adjustment, because it's up to 3.5 to 1, and then we got to change it into an LRFD design. So we're from 510 pounds per linear foot, we have a capacity of 214 pounds per linear foot. Now for the ASD design, similar, we divide by 2, and similar adjustments because of the specific gravity, the aspect ratio, we're at 134. Now you can't say, well, you get more on LRFT because you're not comparing apples to apples. It's just that this is what the capacity is based on the reductions, the similar reductions. Okay, now getting into the shear wall deflection. And for those of you that are familiar with the IBC, there is a 4-term equation that is still in the IBC, but now it's only for staples only under the 2012. But it's a 4-term equation where the first part is the bending based on the deformation of the bending, the boundary members. The second term is shear. Actually, the 2 terms are based on, well, the first one is your shear panel deformation. Then the third term is the nail slip deformation. And then the fourth term is the bending cord slip. And then for those of you that are doing mid-rise construction, this is where you would get, if you're using continuous tie rods, your rod elongation, shrinkage, compensators, and crushing will play into this 4th term. Well, in the wind and seismic provision, we combined this middle term to make it a 3-term equation right here. And so it's a mathematical simplification of that equation and brings in the term apparent shear, brings in that the 4-term into a 3-term equation. Okay, let me go, and brings into the apparent shear stiffness, which is G sub A. Now, one reason is that this provides a linear equation. And so you can see at 0, you apply the load, and you can linearly predict what the displacement is going to be. Now, the curved part of the graph is the 4-term equation. It's a nonlinear term equation, but you can see at strength level forces, 1.4 ASD, the 2 equations are exactly the same. And the difference between the 2 equations further on down is only, when you're doing the calculations, is only about a 1/16 of an inch, which is really very minor given the whole scheme of things related to wood structural panel or shear walls and the construction type. So the important part is that strength level forces, they are totally equal. The other thing to remember is when there was a four-term equations, there was 11 variables, making it very difficult to do the calculations. There was a reiterative, and this simplifies the actual calculations that are performed to determine your wall deflection. So one thing I want to point out is, real quickly, is the three-term equation it's very specific to the nomenclature and the units that are shown in the wind and seismic provisions. In other words, for the width of the wall or the height of the wall, it's in feet. And for the modulus of elasticity of the post, it's in PSI. For the area of the end post, it's in square inches. So it's, in other words, the whole equation, you've got to use the very specific units that are shown here. You can't translate it to inches or all of the equations to inches or all of the equations to feet. It's got to be in the specific units that are shown here. Otherwise, you're going to get some incorrect information. Okay, so given an example, we'll run through this quickly, is that for an 8x8, we have an apparent shear stiffness of 16 kip per inch, and then we have double studs at the end, which gives you a square inch of 10.5 square inches of area. Modulus of elasticity is 1.6 times, 1.6 times to the exponent, anyway, PSI, and then the hold down anchor slip of 0.125, and then induced unit shear, and this is induced shear, not the capacity of the shear wall, and to determine the deflection. So this breaks down each element for the bending and the shear and then the anchor slip. And as you can see, for an 8x8, it's the total deflection is 0.34. So 0.34, and that gives you the actual deflection. The one thing I want to point out is that the biggest contribution to the equation is this middle term, your shear. All things created equal. That is where you can really build in some strength or performance into your shear wall, determining your wood structural panel and your nailing. I mentioned that in the beginning about what provides your strength and stiffness of a shear wall. So that contributes quite a bit to the overall drift of your shear wall. Okay, now going over the three types of shear walls that are recognized in the wind and seismic provision. We have the individual full high shear walls. These are the types of shear walls that have been around for quite a long time. Probably one of the first type of shear walls that are have been accepted into the provisions. And what it is it takes the full height with structural panel. It doesn't take into any contributions for the part of the wall that's above and below the openings. There is a second type of shear wall which is called force transfer around openings, and as you can see, it treats the entire wall as one wall and takes into the contribution of the elements above, the wood structural panel above and below the openings. There's no prescribed method of actually analyzing these type of shear walls. It requires detailing to make sure that this wall acts as one entire wall. It does, however, eliminate the hold downs on either side of the opening. So rather than four hold downs, you now have 2 hold downs. The third shear wall is a perforated shear wall, which is based on empirical based strength and stiffness reduction factors. You're treating it as one entire wall, yet you're requiring that the bottom up plate is is detailed and attached to resist in-plane shear and uplift as well. All of these 3 shear walls have reference design values. Well, you use the shear wall tables in the wind and seismic provision, but the perforated shear wall also eliminates the need for the interior hold downs. Now, if you would like more information on force transfer around openings or perforated shear walls, here's some references that provide you with some information on these type of shear walls and how to analyze them. Okay, I mentioned in the beginning of my portion related to detailing requirements where you have wood structural panels on both sides of these shear walls. In here, if you have wood structural panels on both sides of these shear walls and you have the joint of those panels, in other words, here's a panel, and there's a joint here, and here's a panel, and here's a panel, and here's a joint here, and they land on the same framing members. If your nailing is less than 6 inches on center, then it's required to have a 3-by member there because it could have potential for splitting. So in order to avoid that splitting, we require to have a 3-by member there. Or you can specify that the panel joint locations on either side are offset, staggered, to prevent that splitting of that member. There's some additional requirements in section 4.3.7.1 which has to do with, depending on your nailing of your nails or your spacing of your nails, this doesn't have to do with panels on both sides of the wall. This is where you would join in a panel edge on one side. So if your nailing is at 2 inches on center, or you have 10-penny nailing having a penetration of more than 1.5 inches on center, 1.5 inches, and then you have 3 inches on center spacing. Or if you're in seismic design category D, E, or F, and your capacity exceeds 700 pounds per linear foot, then it's going to require you to have a 3-by framing member. There is an exception to that in that you can have 2 2-bys framing together, so that this allows you, I know in some areas of the country you don't have the availability of 3-bys, so this gives you the out to use 2 2-bys, provided, and this is important, provided that they're connected together. And speaking of which, there is some commentary in the wind and seismic provisions if you are connecting 2 members together and how to calculate the capacity for that connection. This is a really helpful table that provides you, and it's based on the NDS, 2012 NDS, on determining the capacity of the fasteners and what is required. So this gives you some values. The one thing to consider, though, is if you get some closely spaced nailing of this and you're going to want to stagger them, you may want to consider going to a screw type fastener rather than a nail to spread those fasteners out, because closely spaced nailing could cause some splitting. But that's engineering judgment on how you want to approach that connection. This is the section I mentioned about in the commentary where it gives you some guidelines for when you're connecting 2 2-bys together as opposed to having 1 3-by. Now we talked about the adjoining panel edges and where there has been testing and evidence of issues from earthquakes. The other area that we talked about is that bottom plate, and there is no requirement that you have a where you have nominal shear capacities of greater than 400 pounds per linear foot, it's going to require a plate washer, and that plate washer needs to be within 1/2 inch of the wood structural panels. And the reason is because what happens is when that shear wall resists that load, it tends to pull up. There's a pull up, on that pull up on that sill plate and then cause cross-beam bending. So going back to the exceptions, if you're less than 400 pounds per linear foot, it's not required, or if you design the hole down to resist the full overturning and neglecting any dead load. So just to give you some background on the testing that was done and what has been shown going back to Northridge earthquake is that there was some failure in the sill plates. Knowing that, there was some testing that was done, some small-scale testing for this mode 2 of failure. They tested it, but what they found is, yes, there was this type of failure, but also in addition to that, and there was some horizontal fracture also. Now the challenge is that this vertical failure here could be calculated. We can calculate and have calculations to determine when this would occur. However, this horizontal crack in the wood could not be calculated. So this then required more testing. So they tested for this mode 1 and mode 2 to determine how to prevent this from happening. They tested 50, I think, quite a lot of shear walls, and came up with, and you can see some of the brittle failure in the sill plate, doing all types of configurations, all types of capacities, and they determined that the plate, that square plate, was the answer to preventing that type of failure. And remember, we don't want that type of brittle failure. We want to drive the failure into the nails where we can have a ductile failure rather than a brittle failure that you see at the sill plate or a failure at the hold down. As I mentioned before, the aspect ratio, there is a table that shows you what the required aspect ratio is. This aspect ratio is applied differently depending on the type of shear wall you're designing, and I'll explain that a little further in this diagrams. These are in the wind and seismic provision. So we have a BS is for if we're designing an individual full high shear wall. Your BS is the width of the panel and the full height of the panel here, or shear wall. That's what your aspect ratio is based on. Now for force transfer around opening, however, and this is one of the advantages, your aspect ratio is only based on the pier height. So it would be from your height would be that actual window height, and your width would be the width of that pier, as shown here. So your wall pier height is here. However, and the one thing I should note is for both of those two types of shear walls, for example, if this shear wall here did not meet that aspect ratio, but this shear wall did meet that aspect ratio, then that reduction would only be applied to the pier that did not meet the aspect ratio. Now, under the 2008, however, for the perforated shear wall, it's for the entire perforated shear wall that reduction needs to take place. So, for example, your width is B here, and your B is here on the right side, and then your height is that total height. If this did not meet the aspect ratio, but this did, it doesn't matter. That entire perforated shear wall needs to be reduced by that reduction. Now that will change in the 2015 wind and seismic provision, where it would be only applied to the panel or the width of the segment of the wall that does not meet the aspect ratio. So that's one change in the 2015. Now going to the, I'm going to skip this because we're running short on time. I'll skip this poll, so Marcy, don't run the poll. And then we'll get into the wood frame diaphragms. Okay.
Okay, thanks, Michelle. For those of you who are still with us, we're going to just go another 5 minutes or so. If you have the handout and you already have your 90% time in, you will still get your certificate. But if you want to hang on for another 5 or 10 minutes, we'll wrap up here pretty quickly and talking about diaphragms. So the elements of a diaphragm include the sheathing and the chords and the boundary elements. We'll just give a cursory overview, and the tests that we've run show how those diaphragms deform under loads. You can see the load heads here and how those load up, and tests range anywhere from 24 by 24 to 24 by 60 foot diaphragm assemblies. So we've got a really good database to provide for the values that are tabulated in the wind and seismic standard. These cases that are shown here, similar to what we've seen earlier, show the way the panels are laid up on the framing. And so you have your case 1, case 3, case 2, case 4, case 5, case 6, and those then carry into the tables here at the top of the headers, where cases 3 and 4, 5, and 6 are shown here in this top row. And this nail spacing, a question came in a little bit earlier, this nail spacing is the spacing on the perimeter of each of the panels. So if you have 6-inch spacing at the perimeter of each panel, you'd use this column. 4-inch spacing around the perimeter here, 2.5 and 2. And Michelle already talked about how to pick these values out for shear walls, so we won't belabor that. And the stiffness values are shown as well here. Michelle also covered the footnotes, which are very similar for diaphragms, so we won't go through that. You can take a look at these design examples on your own. Again, Michelle did a shear wall example that's very similar to what's shown here, and the specific gravity adjustment factors are also very comparable. The deflection equations, again, going from a 4-term to a 3-term equation, but the 4-term equation is shown in the commentary, and this is an idea of the makeup of that equation. There is a complete example for calculating diaphragm deflection in the wind and seismic commentary, and I think we've got a webinar, an old webinar up on our website under the self-directed study program on this as well, if you want some more information on diaphragm deflection examples. Other things about diaphragms, we do have provisions or tabulated values for unblocked diaphragms with reduced shear and stiffness values. We've got values for high load diaphragms with increased unit shears and stiffnesses. And then something we often get questioned on, especially for existing structures, is the lumber planking or laminated decking. If it doesn't have a high enough capacity, can you use wood structural panels over that? And so there are provisions for that as well, for if you have some retrofit situations that you might be dealing with. So here's an example of the horizontal lumber and then diagonal and double diagonal lumber sheathing capacities that are shown in table 4.2D of the wind and seismic standard as well. Michelle talked about the 3x framing requirements, and so I won't spend a lot more time on that. Very comparable again for diaphragms, and aspect ratios, open front and cantilever diaphragms. A lot of this is changing, especially the open front and cantilever diaphragm provisions in the 2015 wind and seismic standard, and we'll have a webinar coming up on that in a few months. Aspect ratios, again, Michelle talked about that for shear walls. A comparable approach is used for diaphragm aspect ratios as well. Marcy, we're going to skip this poll. 2015 standards are out and available, free download on the website. So if you want to get a sneak peek at what's coming up in 2015, these are all incorporated in the 2015 IBC. And again, we'll have some webinars on those. We've already had one on the 2015 NDS, so if you want to check that out. This one's probably coming up in May or June of this year for the 2015 wind and seismic standard. And so I won't belabor the point here on those. There are some additional resources available for diaphragm design that are shown here, and that'll take us to the end. I know, Marcy, we've run over, so I think we'll have you, if you will, just wrap us up for the day, and I'll let folks know that if you did have questions that weren't answered along the way, we'll be following up with answers to those and getting that information up on our FAQ section of our website. So thanks for being with us today.
All right, that sounds great. Let me switch over to my slides here. I'm hopeful everybody can see that. Let's see, just as a reminder, following today's webinar, you're going to be sent an email. Please give us about a half an hour or more to process the reports and get the links ready to send out. Inside the email is going to be a link to a survey. Please help us by completing this email, or completing that survey for a chance to win a pre-publication. Then second is information about your certificate of completion, and ICC and NCSEA CEUs note that you're not going to get your certificate immediately. That comes in about no more than 2 weeks. Second is the actual certificates will be available within 2 weeks of the webinar. Remember that in order to receive your ICC certificate and quiz link for the NCSEA certificate, you must have been present for 90% of this webinar. That's 108 minutes. Also remember our upcoming webinars and other events reserved next month, March 19th. And don't forget our self-directed studies. Email us at education@awc.org or visit our website, awc.org, for more information. And then let's go to the next one. Remember, multiple attendees. You must be registered on our website in order to receive a certificate. We're getting a lot of people that have registered on our website, or I'm sorry, have an account but not registered. You must do both steps. Okay, so I'm going to leave this up, I think, for a little bit, and that's it for today, folks. Thank you very much for joining us, and have a great afternoon. Thank you.
Actually, I wanted to point out one thing for those that are still listening. There was I think there was a bit of confusion on the height of the structure versus the height of the building. This is just a clarification. The height of the structure is, as Buddy mentioned, there's a structural height in ASCE 7, a definition of that. There's also a building height, which is in the IBC, and that building height is related to the heights and areas of a building that the architect determines. That's from grade plane to the average height of the roof. So 2 different heights, 2 different purposes. Anyway, just clarified that.
Okay.